In this example, we have a sheave that is free to rotate with respect to this payload of 100 kilograms about this point O, and this relative degree of freedom is due to this rotational joint, a revolute joint here, enables that this load is going to move free in terms of its rotation with respect to the sheave, and the sheave is free to rotate in that sense. And it is suspended, the sheave is suspended by this cable, which is considered to be rigid, and then there is this spring which is with a spring constant of K. Now, as soon as we see this figure, what we should clearly identify is that if this mass center or point O, let's say the mass center of the sheave or just point O, moves like an x distance, then it means that this point and that point also moves x distance. In total, this cable in that case should have an extension of 2 times x. Okay, the total length of this cable should extend by 2 times x. What's going to extend here? The spring. So the spring will extend 2x if this O point moves by x terms. So this is what we can see directly from this figure. The other thing that we can see and then assume is that this sheave rotates without slip, and if it rotates without slip, if there is this omega, let's say angular velocity of that, then the velocity that is going to be described for point O, which is going to be the mass center of this sheave, will be related to V by omega r. So that's another thing that we can see directly by taking a look at this system. Then there are this information about the sheave. There's this radius information. So this r information is given to us as 0.4 meters. Its mass is given to us. Radius of gyration is given to us in terms of millimeters, which means 0.3 meters. So with the information of this radius of gyration and then the mass, we are able to calculate the I/O of the sheave as m kappa squared, right? And kappa is given to us as 0.3 and mass is given to us as 50 kilograms. Then there is this 100 kilogram load, and they are suspended by cable and spring, and the stiffness of the spring is 1.5 kilonewtons per meter. Initially, when this system is hung on this cable and then the spring, initially the system is released from the rest, and the spring initially is stretched 100 millimeters due to the total weight of this. Initially, it is stretched as 100 millimeters. Then we are asked to determine the velocity of O after it has dropped 50 more millimeters. O is moved 50 millimeters. That means the spring is further stretched by 2 times 50. So delta X here will be 100 millimeters in that sense, or just 0.1 meters. But then, in terms of calculating the energy stored in a spring, remember that we use the initial energy and then the final energy. So initially, it has already 0. Say X initial is 0.1 meters, and in the final case, X final will be 0.1 plus 0.1, 0.2 meters, which this spring is stretched in the final condition. In the final condition, also, this total mass of 100 plus 50 kilograms is lowered by 50 millimeters. As a result of that, we're going to have a change in the potential energy. And the change in the potential energy will be a negative one because it's dropping. And that potential energy obviously will be stored in the spring. And also some of it will be stored as a kinetic energy. So the change in the potential energy will be the total mass of 150 kilograms times the gravity, and then the amount of displacement in the vertical direction is a negative 0.05. That's our change in the potential energy. From this information, we can calculate the change in the potential energy due to the elasticity. Then the rest is about the kinetic energy. What type of kinetic energy we have due to the translation of both 100 kilograms and 150 kilograms. They have the same speed, so we can assume a kinetic energy of 1 over 2 150 times v squared. This is the velocity of all point. Maybe I write O, but I already specified as v over here. So v squared plus, because of the rotation of this sheave, we're going to have 1 over 2 IO, which we can calculate by using the mass information and then the radius of gyration, omega squared. Now, omega and v are related to each other by kinematics. So we can write this v in terms of omega or write omega in terms of v, whatever we are asked to determine. We are asked to determine the velocity of O, so we can write out this v in terms of omega in terms of v and say this is v over r squared. And then we'll get an expression in terms of v, and this is how you would work out. This is the change in the potential energy due to elasticity, initial condition, final condition for the stretch. And then the potential energy, it has a negative sign because we are dropping, so this is the term for the potential energy due to gravitation. And for the kinetic energy, we have the kinetic energy due to the linear velocity of all point for two masses, and then the kinetic energy due to the rotation, and this Ig, which I specified as IO, it's the same, can be found by m kappa squared. Okay, so that's it. And then there's this kinematic relationship, which we can relate this omega to the velocity of all point, and we can determine the velocity of all point from this equation.